Questions? All right, then let's get going. We're going to start on page 1. Good as place as any. Make sure you put your name on the top of this packet. And you have your notes there to look back on from yesterday. All right, so let's get going. This is review, the first question. An instantaneous velocity of an object is the what of that object with a what. In other words, I'm asking you for the definition of a velocity. Janelle? That would be a vector. This asks you specifically about the velocity of an object. Emily? The slope of an object? How do I find my slope? I don't have a slope. The what? The speed. There we go. It's the speed of the object with a direction. The speed is the magnitude of the velocity vector, and direction is the way in which it's moving. That's what that means. Okay, so a velocity is how fast you're moving and in what direction you're moving. The speed and your direction. All right, let's continue. Question 1. This relates to what we learned yesterday. An accelerating object is an object that changes its velocity. Name 3 controls on an automobile that cause it to accelerate. Name something in your car which would allow your car to accelerate. And we did talk about this in class yesterday. See if you can name one. Olivia, can you name one? Yep. Dakari, can you name another? What else can you use besides the gas pedal to make your car accelerate? You may want to look back at your notes from yesterday, right? Because this was in our notes yesterday. Or at least we discussed it in class together. Whether we wrote it down or not, I know we had a discussion about this because I asked, how many of you are driving or learning to drive? And we had hands go up. Pig? The brakes, the brake pedal. And what is the third control? Caitlin? That's right. Because remember, what is an acceleration caused by? Speeding up, slowing down, and changing direction. Any of those 3 things. So those are the 3 things that would make it speed up, slow down, change direction. Okay, number 2. An object is accelerating if it is moving blank. Circle all that apply. Let me give you a minute to look at that yourself, and then we'll see if you can answer this for me. When is an object accelerating? Is it accelerating if its speed changes? Is it accelerating if it's moving really fast? Is it accelerating if you have a constant velocity? Is it accelerating if you're moving in a circle? Is it accelerating if you're headed downward? Or none of these? Brandon, can you tell me something you circled? Yes, that is correct. There are other things to circle as well. Yeah? If you're going really fast, no. For example, what's a really fast speed? 150 miles an hour? If your car was going at 150 miles an hour on the Northway and you put it on cruise control and you were headed in a straight line, are you accelerating? No, because what is the definition of an acceleration? A velocity change. That means a speed change or a direction change. Just because you're going fast does not mean you are accelerating. Because if I stayed at 150 miles an hour the whole time, I'm not accelerating at that point. There is another one to circle. Nick? A, that's right. That's your speeding up or slowing down, changing speed. Those are the only 2. Going extremely fast, we talked about why that would be incorrect. Constant velocity. If you have a constant velocity, is your velocity changing over time? No. And that's what an acceleration is, a change in your velocity over time. If you're headed downward, it doesn't mean your speed is changing and you're not changing your direction. And F, of course, would not be correct because A and D are selected. All right, number 3. If an object is not accelerating, then what do you know for sure? Only one of these is correct. Which of these is the best choice if you are not accelerating? Okay. B, no. Let me show you an example of that. Right now, I am accelerating, even though I have a constant speed. Why is that? I'm changing the direction in which I'm moving. Let's say I put an arrowhead out in front of me. Every second, my arrowhead points in another direction, even though my speed is constant. Remember, acceleration can be from speeding up, slowing down, or changing direction. So constant speed does not incorporate all 3 of those things. That we want to eliminate all 3 of those. Which is the best choice, which would take care of all 3 of those? Cam? D. The velocity includes the speed and the direction staying constant. And that's why D is the best choice. All right, number 4. Here is our equation for an acceleration. Remember, we learned this equation off our reference table yesterday. A is a change in V over T, which is a final velocity minus an initial velocity over a time. All right, so what does it mean? This is a concept question. What does it mean if we have an object that has an acceleration of 10 meters per second squared? Is that object going to move 10 meters in a second? Is it going to change its velocity by 10 meters in a second? Is it going to move 100 meters in 10 seconds? Or would it have a velocity of 100 meters per second after 10 seconds? I'm going to tell you only one of these is correct. Which one is it, Janelle? B is correct because look at the definition. It's a change in velocity over time. Which one talks about the velocity changing by a value of 10? That's B. B says there is the change in the velocity. 10 over 1. That would be the acceleration. All right. For homework for Thursday, I'm going to ask you to do questions 5, 6, 7, and 8 on page 1. Okay, let's turn to page 2. All right, so let's take a look at question 9. What we're asking you to do here, well, let's take a look at what I'm giving you. I'm going to give you a description of an object moving. And in each of these cases, the object is accelerating. I want to know what is the exact direction of the acceleration vector. Now, yesterday in class, do you remember we looked at that animation of the Hot Wheels car coming down the track? And then we made a list of patterns about how the velocity and acceleration compare when we speed up, slow down, and change direction. You may want to have those patterns in front of you to help you with this. So it's important to understand, is it speeding up, is it slowing down, or is it changing direction to help you figure out the direction of the acceleration? All right, so let's look at A. We have this car traveling to the east. All right, so that is the direction of the velocity vector, east, along Lake Ave, and it increases its speed. I don't even care what the speed changes from. So this object is speeding up as it moves to the east. What's the rule about acceleration and velocity when we speed up? This should be in your notes from yesterday. What's the rule about them? Jules? Same direction. So what's the direction of this acceleration? East, because we said it's headed to the east. B, a car is headed to the north and it skids to a stop. If it's skidding to a stop, what does that mean the car is doing? Slowing down. It's headed north and slowing down. What's the rule about acceleration? Opposite direction. So what is opposite of north? You got it. See, that's what I'm asking you to do for each of these questions. We have an Olympic diver who slows down after splashing into the water. Okay, ask yourself, which way was the diver moving? Not south toward Florida, no. Down towards the ground. That's down. And they're slowing down. So what's the direction of this acceleration? What is it? Up. Yep. Upwards towards the sky. We have a southward bound free quick delivered by the opposing team, and it is slowed down and stopped by the goalie. What's the direction of this acceleration? Alex? Yep, opposite of south, so that is north. We have a downward falling parachutist pulling the cord and rapidly slows down. Yep. Upward, yep. We have a rightward moving Hot Wheels car, which is slowing to a stop. Addie, what would be the direction of this acceleration? Correct. And we have a falling bungee jumper who slows down as she nears the concrete sidewalk. So they were falling and slowing down. Jack, what would be the direction of that acceleration? Up. That is correct. Okay, you are going to do question 10 for homework. Cross this chart out. I don't need you to complete that. And what I'm going to ask you to do on this diagram is the following. You're not going to do the entire thing. But what I'm going to do on this diagram is I'm going to draw at points X, Y, and Z the direction of the velocities. And what I want you to do is draw in the direction of the acceleration vectors for homework on the picture. So at point X, the velocity is headed down the incline. At point Y, the velocity is headed to the right. And at point Z, the velocity is headed to the left. So you're going to add 3 additional arrows with the A on them to show me which way the acceleration is going to point. And they give you information here in question 10 to help you figure out what the car was doing. Was it speeding up or slowing down at each of those points? Okay, let's go to page 3. On page 3, question 1 is showing you various ticker tapes. Below each ticker tape, I want you to tell me how that car is moving. Specifically, is it speeding up, is it slowing down, or is it moving with a constant speed as it goes from the left to the right? Then, I want you to tell me if that car has an acceleration. And if so, what is the direction of that car's acceleration? Okay, so let's look at A. Look at the distance between these cars. Is that car speeding up, slowing down, or moving with a constant speed? Constant speed. Can you tell that? Equidistant. So we have a constant speed here. Remember that ticker tapes don't tell us anything about the direction or changing directions. All we can see are speed changes. But on all of these, the car's headed to the right. So this is a constant speed to the right. If you have a constant speed as you move to the right, are you accelerating? Yes or no? No. So is there a direction? Nope. All right, look at ticker tape B. What is this car doing? Brandon? It is speeding up. How can you tell that? Yep, the distance from car to car gets bigger and bigger and bigger each time. So, is there an acceleration if you are speeding up? Yep. What is the direction of that acceleration? That's my next question. Alex? Yes, I'm just going to put an arrow showing it going to the right. Because when we speed up, it's in the same direction that we're moving in. What about C? What is that car doing? Nick Rushford, can you tell me? It's constant speed. That is correct. Purnima, does that mean there's an acceleration? Yes or no? Correct. So there's no direction. Let's look at D. What is this car doing in letter D? Dakari, can you tell me? Yep, it is speeding up. How can you tell? Yep, this distance is less than this, which is less than this, which is less than that. So it's the distances are getting gradually bigger. Is there an acceleration, Josh? And what would the direction of that acceleration be? To the right. Very good. All right, let's look at E. Savannah, what is this car doing in letter E? Yes, how can you tell? That's correct. The distances are getting smaller and smaller. So is there an acceleration? Who can tell me? Yes, there is. What is the direction of it? Do you know? Good. I'd like you to do question 2 on that page for Thursday. Okay. Can we turn to page 4? We got to get through page 5. So let's go to page 4. On page 4, I also want you to do question 3 and 4. Okay. Let's go to question 5. This one we're going to do together. Notice in number 5, it says, think about this name. This website, the Physics Classroom, where I got this worksheet from, likes to do a lot of play on words with the names. This is kind of an unusual name of a person. Renata Oil. Her car has an oil leak. What do you think's going to happen to her? Her car has an oil leak. Be more specific. She is going to run out of oil. You see that? You get it? Renata Oil, run out of oil. Listen, I can only make this class so interesting at this point. So we try to introduce some, if you see a name of a person in a question, you got to be going, where is this supposed to be funny? All right, that's all I can do. Okay, we play with toys. So now we're going to throw some funny names at you. Her car has an oil leak, and it's leaving a trace of oil drops on the streets as she travels through Glenview, which is the name of the city where this particular website is created, Glenview High School outside of Chicago. So a study of Glenview's streets reveals the following traces. I want you to match the trace with the verbal description. And then it says for each match, verify your reasoning. You don't need to do that. So basically, you have to tell me which ticker tape goes with which description. And we're going to do that over here. So let's look at the first description. So Renata was driving with a slow, constant speed. Then she decelerates to rest. She remains at rest for 30 seconds. And then she drives away really slowly at a constant speed. Which of these 3 ticker tapes matches that description? Brandon? C, yes. Because here we see a slow, constant speed, but then notice they get closer and closer here, and then eventually we end up with a puddle where she was at rest for a while, and then she travels away again at a constant speed, but notice this speed is even less than what she started with. So even though this was slow, this is really slow. Number 2, Renata rapidly decelerated from a high speed to a rest position, and then she slowly accelerates to a moderate speed. Which one shows her decelerating from a high speed to rest and then slowly accelerating to a moderate speed. Emily? Yes. Slowing down, stopping, and then speeding up, in other words. Number 3, she's traveling at a moderate speed and slowly accelerating. Well, which one's left? B. Here we see a slow, constant speed, but then they gradually get further and further apart, so it shows a slow acceleration or a small acceleration. Okay, let's go to page 5, which is the last one before we begin our review for tomorrow's test. All right, first of all, number 1, I'm showing you 3 data tables. And notice that it says here that the motion is uniform for all 3 of these, which means that the speed is constant. The velocity of these objects is constant. I want you to look for me what the patterns are in the table. Fill in the blanks in the table by locating the pattern. So can you tell me what should go in blank 3? And you do have a calculator, right? So you can use your calculator if you need it to help you come up with the numerical values to complete the patterns. What's the pattern in the first table for the giant sea turtle? Each value is going up by what? 0.23. So the value at 3 hours should be 0.46 plus 0.23, which is 0.69. What's the last, or the value at 5 hours going to be? 1 point, yeah, and at 6, 1.38. Okay. Now below it, I want you to tell me what speed this turtle had in miles per hour. What was the turtle's speed in miles per hour? This is pretty easy because how much mileage did the turtle do in 1 hour? That will tell you the answer to that. Janelle? Yes, because she went from 0 to 0.23 in 1 hour. Take that distance and divide by that time. So 0.23 miles per hour. MI over HR. All right, let's do the same thing for the cheetah, please. Figure out the pattern. If you have a uniform speed, the increments should be the same. Position change over time. And you should get the same values I got. What is the cheetah's speed in meters per second? So go to 1 second. Tell me what the speed was. Ashley? Yep, 25.0 meters per second. Because if I go to 1 second, I see it went 25 meters. So 25 over 1. It's the easiest way to do it. All right, now let's look at North America. This is the speed for continental drift of our continent. Can you figure out the values in that chart, the pattern? And then can you tell me what the speed is in centimeters per year? Cam?
1.00 centimeters per year.
That's correct. Everybody okay with that? This is review. This will be on tomorrow's test because it's uniform motion, which is what Unit 2 is about. Number 2 is about the new stuff. Again, we're looking for the patterns in the chart. Let's do the first one. These are positions per day. Do you see what the pattern is in this chart? What do I have to do to come up with the next position here at 2 days? You want to just do it? Okay, I'll just freeze the screen. Just do it. I want you to do these two right here, the snail and the Honda Accord. This one you're going to do for homework, but these two we're going to check them in a minute. Let me just let you do it, and then we'll check it over. How'd we do? I haven't shown you my answers yet. Let's look at the snail first. These are the positions 0, 11, 22, 33, 44, 55, 66. Do you notice that the position increment is the same every day? That means you're not accelerating. That snail's moving at a constant speed. So there is no acceleration. You gotta know what it means. Constant speed means no acceleration. All right, let's look at the chart for the next one. The Honda Accord. 60 to the east, 54 to the east, 48 to the east, 42 to the east, 36 to the east, 30 to the east, and 24 to the east. This car is accelerating because the velocity in miles per hour is changing every second. How much is it changing by every second? Josh? No. Shoot. Yes, it's changing by 12. Now, what is the direction of that? So what is this car doing? Speeding up or slowing down? So what's the direction of the acceleration? To the west, opposite of what you see here. So that acceleration is 12. Oh, and it's not meters per second squared. What are the units? Miles per hour per second. And the direction is west because it was slowing down. Everybody follow that? Okay, you have to do the Falcon for tomorrow. Thursday, our next class period.